also with the most appropriate approach of alpine-side. Now we need to close very simply what is going to happen when the discontinuous fiber reinforced lamina is not reinforced in a way three elastic constant, which are the Young modulus, the shear modulus, and the Poisson ratio. Remembering that of these three elastic constants, just two are independent among them. And the most used, I leave to you, model, which is used for the estimation of the Young modulus and for the estimation also of the shear modulus, and then the calculation, if you want, of the Poisson ratio, are those here reported, which are known as also Pagano models. So the basic assumption is quite simple. I mean, having fixed the materials with which we have fabricated our composites, that is the matrix type and its properties, and the fiber types and its properties. In the case, we have the fibers which are randomly oriented. I make an estimation of the Young modulus of the randomly reinforced fiber lamina, fixing my axes, which are again axis number 1, or if you want an axis X, and axis number 2, or if you want axis Y, you can also put 1 here and that is here, and 2 here, it doesn't matter. And by considering two subcases, the first cases is those for which we think that the same percent of reinforcement, which is effectively randomly oriented, is, let me say, distributed in an aligned way. And so we can make with the equations that we have already seen, the estimation of the Young modulus on this direction, which will be EL, that is longitudinal, and which in our case here reported is A11, and at the same time also the estimation of the Young modulus in the two direction, that is AT, and then it's equivalent to A2 and or A22. And with these values and with this simple formula, we can have an estimation of the Young modulus of the randomly oriented. That is, we have contribution from both sides. With this, we can have an estimation of the shear modulus for the, again, random oriented. And then with this basic equation, which applies for isotropic, as I said to you, and homogeneous materials, we can have an estimation of the Poisson ratio. With this, the micro-mechanical approach for the study of fiber-reinforced lamina in a continuous way or discontinuous way, randomly oriented or with discontinuous fibers aligned, can be considered closed. And then we have to make some merge with a macro mechanical approach, that is the macro mechanical behavior of a lamina, which is not a, let me say, a duty of this course, because it has been explained to you in other courses of your degree course. So I just make some a short review of these, which have been already studied topics by other courses inside this university. And just to fix the items and to show to you how the micro mechanical approach, which is more proper approach for a material science and technology lecture, can be coupled with a macro mechanical approach. Well, if we are in a three-dimensional, generally speaking, in a three-dimensional space, which now we fix again with the axis 1, 2, 3, what we can remember, if we are dealing with mechanics of materials, in the case of linear elasticity, that we do have, as we said, a tensor of the stresses, a tensor of the strains, and then we have a stiffness matrix. And the relationship is given by the expression which is reported here. That's generally speaking. Now, this general formulation is a formulation which applies without any simplification to materials which are anisotropic in behavior. Then we have some subcases, including, as in this model, obviously, the 1, 2, 3 three-dimensional space, which can be also x, y, z, just the same. The case in which we do have an orthotropic materials in the 3D space, again, and we have defined this at the beginning of our discussion on mechanics of composite materials. In this case, we do reduce the matrix, the stiffness matrix, to 9 independent elastic constant. And by the 0 that you see here, okay, it is evident, since we are in the case of orthotropic materials, but now also with the assumption that we are going to apply loads only on principal direction. Now, meaning of 1, 2, 3 is important as axis. We do not have, as we already said, interaction between normal stresses and shearing strains. Instead, it occurs in materials that do have an isotropic behavior. If we move to isotropic behavior, we have further simplifications, and in this case, always in a 3D space, we do have just 2 independent constants in the stiffness matrix. Now, our aim is to understand if the values of this stiffness matrix or of the compliance matrix, that is the matrix for which we can write down the relationship between the strain tensor and the stress tensor, can be coupled with our estimation of elastic constant that we made by using the micromechanical approach. So for isotropic materials, we can also write the compliance matrix, which is usually defined with the term S, and which you see, it's a matrix for which we are making relationship between the strain and the stress. In this case, we need to change the terms inside the matrix, because that one we have seen before, they were related to the calculation of the stress, known the values of the composing the strain tensor. So for orthotropic materials, again, we have 9 independent constant. For isotropic materials, again, there is no reason to change if we invert the relationship to independent constants. And these are the formulation of the compliance matrix. The meaning general of the terms of this S matrix is what is reported on this slide. So this term S11, S22, and S33, they represent the extensional response, because we have epsilon here, to an individual applied stress along the direction 1, 2, 3, respectively. This S44, S55, S66, they represent the shear strain response, since here we do have the shear deformation, to an applied shear stress in the same plane. And then we do have this fourth part of the, that is S12, S13, and S23, that represent the coupling between the similar normal stresses and normal strain, extension, coupling, more commonly known as Poisson effect. Instead, this part in yellow, the terms that represents the normal strain response to apply the shear stress. What is going to happen for the materials having a non-isotropic behavior, and is what we have called, so the same applies also to this part of the matrix, what we have called the shear extension coupling. That's the general meaning and meaning of the terms which are reported inside the compliance matrix, the general compliance matrix, for which in some cases, like we have just seen here, or like we have just seen here, orthotropic or isotropic materials, we can have zero value depending on the material's behavior itself. If we are going to make some example to be a little bit more clear, this means that, for example, if we take an orthotropic materials element, which is subjected to uniaxial tensile loading in the principal direction 1, longitudinal, we call direction, that is the direction of a ligament, of the fibers, we can write very simple relationship, which are coming from the general approach that we have seen, for which the shear coupling is equal to 0. And so if we have just sigma 1 value, this means that we can calculate the deformation, that is the strain in the one direction, and then the effects which are related to the Poisson ratio, that is the contraction, which are going to happen, for example, in the direction number 2, as we have seen, as we have already seen. And so if we remember that, and we know because we are talking about a linear elastic behavior, remember, so we have the hook law that can be applied. If we remember the general expression for which the strain can be given by the stress divided by the Young modulus, and we remember also the meaning of the Poisson coefficient that we have just recalled, with this condition, because there is no shear in the case of applied load in a uniaxial way in the one direction, we can derive, we can calculate the value of the S11, S12, S13, which are, let me say, values that we can put inside the compliance matrix. Let's take this general, okay? Because we have seen that, again, here we do have, that's our cases, 0 value in many positions. If instead we are going to apply a tensile load in the transversal direction, that is in the direction number 2, we do have, again, in a similar way, the possibility to define the 3 strains according to the 3-axis 1, 2, 3, being again not present a shear coupling. And so now what is, let me say, leading is this expression, which comes again from the application of the linear hook law, and then the possibility to have the contraction in the other direction defined by the relative Poisson ratio. And so being valid, this simple equation, this means that we can also define the values of the terms S12, S22, and S23. Being in this case a 3D, let me say, approach, not an in-plane approach that we will see later, we can repeat this thinking about the application of a normal loading, again tensile, in the out-of-plane transfer direction, that is along the axis 3, which would be in some cases the axis Z. And so as you see here, this is the leading, let me say, expression, again, this is 3, again by using the Hooke law, and then we can estimate the value of the strains in the direction 1, 2, 1, 2, being again the value of the shear strain equal to 0 by using the relative values of the Poisson ratio. And this allows to us to make a calculation of the coefficient S13, S23, and S33. And so we can populate, let me say, our matrix, but in order to complete the population, we need to take into account also the possibility to have an application of pure shear loading. So, for example, if you apply a pure shear loading in the plane 1, 2, in this case, we have just this deformation shear gamma 1, 2, and all the other one at 0, because we are talking about orthotropic materials, no shear coupling. This is the, how to say, the Hooke law, which is written in the case of shear deformation. You see here the shear modulus. And so this allowed to us to obtain this relationship in order to calculate the value of S66. And similar conclusion can be obtained in out-of-plane pure shear loading, that is 1, 3, and 2, 3 planes, with the definition of the terms of the matrix, which are S4, 4, and S5, 5. And so, if we want to express, let me move this, no, it's impossible. We want to express our compliance matrix completely, remembering also that there is the validity of this, we have already used, relationship. The SEJ matrix, as it is written by a mathematical formula, is given by the terms which are reported here inside, with the 0, which are telling us that we are applying loads in the principal direction, and so we do not have a shear coupling. And so, as you can see here, in order to put the value inside the matrix, the real value, we need some model that could be also an experimental results, but we can need also models according to which we can have an estimation, for example, of a 1 or a 2 or a 3, and this comes from the mechanical approach that we have seen at the beginning. Terms which are, let me say, also used if we want to write a relationship between stiffness and engineering constants, led to this set of simple transformation of equation, which is reported here. Remember, just to be clear, that the C constant are this one, that is that one for which we can calculate the stress knowing the strain, and instead the S constant inside the matrix allow to us to calculate the strain knowing the stress. And so very simply, we can also, if we need it, to have the possibility to define these terms, which comes from very simply by the inversion of the compliance matrix to get the stiffness matrix. And so these are the final results in which obviously again they appear the basic elastic constant, which can be estimated by using the micro-mechanical approach, or I repeat, can be estimated in the sense that can be calculated by experimental laboratory testing. Now let's move a little bit. I see, and how this approach can be again simplified when we are going to talk about anorthotropic materials, which is our case, which can be classified as the basic element of a composite materials, a multi-layered composite materials, which is the lamina. In this case, what we can make as hypothesis is that we have a plane stress state, and thus this means that we can say that along the axis number 3, for what it concerns the normal strains and for what it concerns also the shear strains, they can put equal to 0. And so our, let me say, our relationship can be further simplified as it is written here, and we are going to move from a three-dimensional problem, which is a general approach, to a bidimensional problem. This is allowed to us because we expect giving the peculiarities of the single lamina, that the lamina is essentially stressed only in a plane stress state, because that one are, let me say, the direction on these planes for which the lamina can show its fundamental capability, that is of the concept of composite materials. And so if we are going to use the notation of principal direction, our stress-strain relation can be reduced to this one, no shear coupling effect again, and this in terms of compliance matrix, with this, which are derived by the previous expressions, which are the estimation of the values of the matrix itself, or if you want to write it in the stress-strain relation, we usually use as notation the definition of the Qij matrix, which is called also the reduced stiffness. Why reduced stiffness? Because we have made the hypothesis of an in-plane stress state. And from the previous, that is from the general approach, we can also define which are the value of the reduced stiffness matrix, which are reported here, or in terms of engineering constant, again, the constant which are estimated by the macromechanical approach, we can write the Q coefficient which populate the matrix as it is here reported. And here, as we said already, we have, in this case, with a plane stress condition, 4, not 9 for aortotropic, but 4 independent elastic constant, which are the two Young modulus in the longitudinal and transversal direction, the Poisson ratio, and the shear modulus on the plane 1, 2 for both. And which were, if you make a link, exactly, let me say, the topics of the main estimation allowed by the micro-mechanical approach. Here you have some value, just to some special condition, but just to have an idea for different systems. For example, for glass epoxy with 45% of fiber volume fraction, or boron epoxy, or graphite epoxy, you see they are all polymeric matrix composites based. In terms of modulus and in terms of other properties, like, for example, thermal expansion coefficient or coefficient of moisture expansion. That's very important for a unidirectional lamina. Okay, just to have some figures, just to have an idea. If we move in the case of isotropic materials, again, with the assumption that we do have a plane stress state, we do have a further simplification, as in the general case. This is the compliance matrix, this is the reduced stiffness matrix. These are the relationship which allow to us to calculate the values of these two matrices. And as you see here, we are going to reduce the number of elastic constant because we have made, in this case, the hypothesis that we do have anisotropic materials. Why I tell to you also the isotropic materials? Because if, for example, we are going to have a multi-layered composite materials made by single lamina, which are reinforced by discontinuous reinforcement disposed randomly inside the lamina, the first slide that we have seen today, we can follow the approach of the isotropic materials. As we have already seen before, we can have an estimation of a Young modulus of this particular lamina, shear modulus of this particular lamina, as well as a Poisson ratio of this particular lamina without any reference to the principal direction 1 or principal direction 2. So it can be used, this approach, not only for pure isotropic materials, like, for example, common metallic alloys, but also for composite materials in the case we do have, for example, lamina which are reinforced by short, randomly dispersed fibers. This is the reason because I tell to you also this one. Then we have made the hypothesis up to now that we are loading along a principal direction, but this is not always the case. And so when the principal direction of orthotropy of the materials, which is our basic element, do not coincide, they are not the same with the coordinate direction, which are the natural, let me say, approach for the definition and the solution of the problem. And so if we say, for example, we are going to apply a load on the X direction or on the Y direction, or for example, a shear on the XY plane, being X and Y not the same axis corresponding to principal direction of the lamina, well, we need something which allow to us to make this evaluation, because if we are not loading on a principal direction, well, the simplifications that can be carried out by the behavior of the orthotropic materials cannot be used in our in approach. And so we need a method essentially to transform, as is written here, stress and strain relation. This is an error, a relation, okay, from one coordinate system to another coordinate system. So we must to some way link the behavior depending on the theta angle which represent the difference, let's say in this way, or the rotation if you want, between the natural XYZ system, coordinate system, and the principal 1, 2, 3 coordinate system. And this is quite simple, because if you remember that if we have a force applied, a load applied, well, we can decompose this load applied depending on the value of the theta angle in the component, which can go rise to a shear or to a tensile load or to a compression load, that depends on the sign, on the principal direction. And so in order to move from the XY system, if we are in a plane stress state, to the 1, 2 system, we just need to use trigonometric function. And so this is the relationship which are known in order to put in relation stresses which are calculated on a general XY plane system with stresses which are referred to the 1, 2 coordinate system, or this is the relation for which you have already started. We can move from the 1, 2 coordinate system in terms of strain to the XY gamma XY strain in the XY reference system. You see here we just have trigonometric function. which are related to the angle, this angle of rotation of the system 1, 2 with respect to the system XY. And this can give rise to a mathematical approach which led to us to write down, having defined this as the transformation matrix, as it was in the previous slide, with the relationship written in a mathematical, let's say again, approach, in which you can find the inverse of the transformation matrix, but it's just a concise method to write the expanded that we have seen before. If we use then a simple matrix which is called R, written like this, with the figures number 2, which is used because of this relationship you see here, it takes into account 1/2 of the shear strain on the XY plane. It can be written also like in this way, okay, or in this way, okay. Just mathematical modeling. And in the case of our case, that an orthotropic lamina, then the situation can be defined by looking to this general expression. You see, we are again using what we have said before, but here we are making the simple case in which 1, 2, 3, or 1, 2 in this case are the same of XY, and then the general coordinate system. And so from this, it comes from a series of mathematical equations like those here reported, in which we have the transformation matrix, in which we have the stiffness matrix, in which we have the R matrix as we have defined, and all these system give rise to another matrix which is called transformed reduced stiffness, which comes by multiplying the matrix that are reported here, with which we can link in a general coordinate system the values of the strain in this coordinate system, which is not coincident with the principal. The coincidence is that peculiar case which can be described also by this equation, but this is the general formulation, the strain with the corresponding stresses on in plane, obviously, again, stresses. And by coupling all we have seen, the values of the reduced, this Q underline, overline, sorry, IJ terms, that is this one, okay, they can be written, as you can see, by using the standard Q value and by using the corresponding result related to the use of the trigonometric function, which obviously depends on the value of the theta angle. When theta is equal to 0, the reduced matrix Q we overline is coincident with the reduced matrix just Q. And the same approach we can make if we are going to talk not about the stiffness, but about the compliance. Again, general formulation is this. So we have, let me say, the reduced compliance matrix. We have the expression which comes from the value which are referred to the principal direction with the trigonometrical function. And again, when theta, the angle theta is equal to 0, these two terms are going to be coincident. And thus we have the possibility with this to enter in the classical lamination theory. And in the classical lamination theory, just very quickly, because you have studied this in other courses, as I told to you, we have some basic assumption that I have resumed here. And in this basic assumption, we say that each lamina of the laminate is quasi-homogeneous, but essentially is orthotropic. So we are going to overimpose one lamina on the other one. And then we introduce also the angle of orientation. Another important thing that we need to remember for this kind of modeling, which is again an elastic modeling, okay, is that we can accept a continuous variation of the displacements through the laminate. That is, we cannot accept the discontinuity in terms of displacement, that is, in terms of strain through the laminate, because otherwise we have broken the interface between two adjacent lamina. But this hypothesis comes together instead with the possibility that since we are going to change the elastic, macroelastic properties of the lamina, depending on the orientation and the direction of application of load, that we will have discontinuity in stress. So continuity in displacement, in strain, and discontinuity in stress or force, which is loaded by each single lamina. And the general approach puts in relationship, let me say, the values of the strain inside the laminate to those which are referred to the plane strain, the reference plane strains, together with the terms which is terms linked to the so-called matrix, curvature tensor. Z is instead the z-axis, so along, let me say, the through thickness axis, this one, okay? And so this is the basic approach in terms of laminate when we put together different lamina. And again, also in this case, for the general K lamina inside the composition of our laminate, we can write the equations that we have seen before, and we again make this assumption of the plane stress state. Terms are essentially the same of before, and so we can move through this approach inside each layer and have an estimation inside each layer of the relationship between strain and stresses. And we can expect, going to look into our assumption, we can expect, you see here, a strain distribution, that is displacement, which gave rise to displacement, which is continuous, you see, varying through the laminate, but continuous. But this with discontinuity in stress distribution. So strain continuous, but stress discontinuous, because if the lamina 1 it has properties A11, and if the lamina 2 has properties A11 of the lamina 2, which are different, obviously, depending on the orientation, that's a general approach. Obviously, in this case, let me say the values of the strain must be different. Then, again, a recall, we can introduce, let me say, this model, for example, which was explained in the previous slide. We refer to the mid-plane, because we are usually using symmetric disposition of the layer, and can have, by using the macromechanical approach, an estimation of a strain distribution in the case of elastic behavior of our system, and in the case in which inside each lamina we can made the assumption, that's the simplification approach, simplified approach of a plane stress state for the evaluation of the distribution of stress strain in the single ply. Then that's normal, you know that one. From the evaluation of the strain, we can make the integral, so we can make also an evaluation of the forces of the moments which are present inside the single lamina. And so we can write also our expression in terms of finite quantities, that is by using the integral inside the single lamina and the single ply. Ply and lamina they are synonymous in this case, to have an idea of the resulting capabilities in terms of supporting applied loads by the laminate. So that's classical, I don't know to say, construction science, something like that, that you have seen some years ago by other colleagues with respect to myself. And so going on in order to have the complete possibility of model also a laminate. We can have shear extension coupling, we can have bending extension coupling. That depends on the way in which the laminate is fabricated, and this is the general final, let me say, approach for the modeling in these cases, where you see we have in terms of forces, normal momentum, and then we can have also coupling when it is existing, depending on laminate orientation. The laminate orientation is usually defined by using a specific code, which is the so-called laminate code, so that, for example, this is a way to represent a laminate. In this case, we have 1, 2, 3, 4, 5 plies, that is 5 lamina, which are going to represent our total laminate. And when we use this expression, that is 0, minus 45, 90, 60, 30, which is reported by bracket like in this way, this means that this force layer 1, according to our coordinate system, is a layer for which, for example, if this is our coordinate system, okay, for example, fibers are aligned along the X direction, okay? We are not going to take into consideration Z for the reason we have said before. When we move to minus 45, this means the fibers are aligned with respect to the X direction at minus 45 degrees. Then we have orthogonal, that is 90. Then we have 60 degrees. Then we have 30 degrees. And you see, in this case, when we, for example, think to apply the load here in this direction, just to make an example, this lamina will show on this direction different properties in terms of response with respect to the following minus 45 or 90, because in this case, let me say, stresses are oriented through a principal direction. In these other cases, no, and so we need the matrix transformation and the necessity to use also the theta angle as we defined before. That's another example in which we do have 1, 0, 1 minus 45. You see here, we do have two, in this case, two plies, two lamina, which are both at 90 in terms of degrees, in terms of orientation. And so the laminate code is usually written in this way. And the last one, which is not in terms of value inside, but which is as general case, the common approach, is those of a symmetric laminate. This is the axis or the plane, if you want, of symmetry. And you see here, we have 60, 60, minus 45, minus 45, 0, 0. And in this case, in the case of the symmetric laminate, the notation, the lamination code is the same of the other one. While we do not repeat all the 6 plies here, we just repeat the first 3. That's a case that the first one is 0. It could be also -45, and -45 would be here at the bottom with S here. It's written S just to understand, to define that this subscript S, which is put outside the brackets, tell to us that we are in a symmetric situation. And this is another possibility. And there are also notation in which we have hybrid laminates, that is, for example, laminates for which we are going to change usually not the matrix, which is for our structural components epoxy, as we have said, but the reinforcing phase. In this case, you see here we have graphite at the outer, as well as here, and then we have boron, and so it is used a notation like this one. Again, we do have a symmetry in this case, line of symmetry, plane, if you want, by putting inside the brackets a symbol, in this case GR, which stands for graphite, and B, which stands for boron, in order to remember that the plies, in this case, are made by the same matrix, but it is changing not only the fiber orientation inside the single plies, but also the materials, which is going to represent our reinforcement, graphite in the first case, and boron in the middle in this case specifically. And this is a code which is usually used in order to indicate our laminate, I would say, distribution or geometrical properties. Having known this one, and then we can go enter inside, the micromechanical approach in order to have an estimation of the properties of the single plies along its direction, principal and general XY, and then we can combine this micromechanical information into the macromechanical model, which allow to us to make a calculation on the stress-strain distribution inside the composite materials, inside the single plies of the composite materials, supposing the application of a defined load. Remember that all this works quite well. In the case we can rely on the assumption that we have made, many assumptions, linear elastic, etc., we have told many times. And in the case in which is reliable, we assume that we can accept stress. There is no way to overcome this stress discontinuity, and we instead use deformation, that is strain continuity. And with this, our discussion about mechanics of composite materials is concluded. So if you have questions, I'm here to answer to you. Okay, if no questions, have a good weekend, and we will meet again on next Monday. I will be in the classroom because I have seen there are 2 of you which will be present physically. Okay, have a good weekend. Bye-bye to everybody.